So one of the most important things to learn, being a chemist or a scientist or whatever, even, whatever you're to be doing, nurse practitioner or a physician or a pharmacist, knowing what measurement actually means, knowing what the limitations of whatever particular sort of measurement it is you're doing, and being aware of the uncertainty involved in measurement. Because when you measure something, there is always error. You could be using, I remember I had a piece of equipment at UCLA that cost $2 million and was able to give measurements with like less than 1 part per billion, but it's still an error. So you still have to know exactly what it is you're using, where the errors come from, and what are the uncertainties involved. And this usually comes into when you're running a lab report. One of the key things you want to include in any lab report: what were your sources of error, and what did you do, to deal with them. So we'll talk about some of the experimental errors that come up. And when we say errors, it's not like, we're, waving a finger at you and saying it's your fault. It just comes from the nature of doing science. There's going to be errors. There are no exact answers. So any lab you do, any sort of experiment you do, is only as good as the data you get, right? I mean, that seems reasonable. But anytime you do an experiment, say you write a scientific paper and you publish it, you have to say what the sources of error in your data is, how you measured that error, and then how you attempted to make corrections based on that error. So that lends credibility to your results. If you can say that the answer is 10 plus or minus 0.1, that's good. Everyone said, oh, okay, I understand how precise that is. If you just say the answer is 10, nobody knows what that means. Is it 10 plus or minus 1, plus or minus 10? Is it closer to 10 than it is 100? We don't know what that means. So always having some estimate of what your error is critical. So there's going to be systematic errors. So these are errors that you sort of figure out when you're initially setting up your experiments. The classic example of a systematic error is something that you can detect and then fix. You can fix these things. For instance, a miscalibrated instrument. Anyone can tell me what calibration means?
It's like zeroing out something that's used to measure, yeah, I don't know.
That's close. I mean, that is a systematic error. It's not quite what calibration means, but it's close. Who's used a pH meter before? Anybody used a pH meter? Okay.
Acidity, or
right. Yes.
Yeah. Mm-hmm.
Or let's say a digital thermometer. A digital thermometer. You take a digital thermometer, you put it into, water or something, and you press the button and you ask it what temperature it is. Well, your digital thermometer doesn't know what temperature means. It has no idea what temperature is. It's measuring something and then converting that into a measurement of temperature. And so what you need to do is a calibration, and you would calibrate it by basically putting it into something that you know what the temperature is, and then telling it what the temperature is, and then putting it into something else. So an example would be, let's say you put it into some ice water. So what temperature is ice water? What's the temperature of ice water?
I mean,
Zero.
Zero, right.
Okay,
0 degrees Celsius. So basically you would put your thermometer in there and you tell it that is 0 degrees Celsius, because it doesn't know it's 0 degrees Celsius. They just say that's what it is. Then you put it into some boiling water. Now, what's the temperature of boiling water?
100.
That's 100 degrees Celsius, exactly. So you put it into 0, you say that's 0. You put it into 100, you say, okay, that's 100. So then when you measure the temperature between 0 and 100, it should be very accurate, because it now knows what 0 and 100 precisely is. So that would be the idea of a calibration. It's basically telling an instrument what it should be measuring and then making sure it's measuring it correctly. So if you have an error like that, those tend to have good precision, but poor accuracy. Now, what's the difference between precision and accuracy? What does precision mean?
Precision means like this very it means a small increment, like when you're measuring, like it's it's a consistent measurement.
Exactly, that's what
Yeah.
it means, consistent. So for instance, if I was like taking the temperature of boiling water and I got 100.0, 99.9, and 100.1 in 3 different measurements, I would say that was very precise. I was getting the same, very close to the same answer every single time. Now, what about if I got 89.9, 90.1, and 90.0? Are these answers precise?
There's another name for it. I don't remember. It's right at the top.
Are they precise or not? That's the question.
No.
Yeah.
No?
I'm saying yes, and I'm hearing no. So what do we think? Yes or no? It's a definite yes or no question.
I guess 90.0. Yeah, it's precise.
It's precise. Yes.
Yeah.
The
Okay.
answer is yes, it is precise, because you're getting very close to the same answer every single time. But the question, is it accurate? If you're measuring the temperature of boiling water and you got these 3 numbers, would that be accurate?
No.
No, it's
No.
not accurate.
No, it isn't. Now, let's give you another example. Let's say I'm measuring the temperature of boiling water and I get this. I got 90, I got 101, and I got 109. Are these numbers accurate?
No.
I seem pretty quick with that. I got neither. Ooh, neither. I like that. So we know they're not accurate because they're all over the place. I'm sorry, we know they're not precise because they're all over the place. But are they accurate? I got a neither from Brandon.
They're not very close to each other, so wouldn't it be?
They're not very close to each other. So if they're not very close to each other, we know they're not precise. So that is a given. But are they, can you be not very precise and yet be accurate? It's a deep question.
Can it be accurate if one of them is kind of close to like the actual value it's supposed to be?
That's a good question. Well, the thing is, if you got 3 numbers like that, you wouldn't know which one of them was correct. Like generally, when we do experiments, we usually do them in triplicate or in quadruplicate. And so if we do like 4 examples, and 3 of them are very, very close to each other, and one is completely different, you just throw that one away, and you say that one is an outlier because something went wrong. But if you have three numbers like this, you have no idea which one is correct. So you really couldn't throw any of them away. But if I averaged them, I'd get pretty close to 100, don't you think? If I took the average of 90, 101, and 109,
Yeah.
it'd be almost exactly 100. And so my answer would be accurate, but it wouldn't be precise. Now, obviously, as scientists, we'd like to be both, if at all possible. We'd like to be both precise and accurate. That's the best of both worlds. But generally, we'll take accurate over precise anytime, because it's very embarrassing to be very precisely wrong about something. On the other hand, this made whatever you're using to measure something, maybe only this good. That might be the best you're going to get, depending on what it is, what instrument you're using, or what sort of measurement you're getting. For instance, if you're dealing with like large populations, there's going to be huge amounts of error dealing with large populations. You may not get like super precise answers, but you can get accuracy. And that's really, at the end of the day, that's more important. Okay, so random errors. These are different from systematic. So these are errors resulting from either from like reading or interpreting the value from the instrument. These come from like, basically it's both the instrument and you. Like you can't get an accurate measurement from the instrument as you want, because maybe it's not the right instrument to use. And then you sort of have to use your own judgment in determining what the measurement should be. Like reading the volume from a graduated cylinder, for instance. Like that's something we're going to do today. So if you have a graduated cylinder and it has marks on the side to tell you what the volume is. Well, what if you get your meniscus comes right in between two of them? That's like, let me draw it a little bit better. So here is 5 and here is 4 mils. Now it's up to you to determine, well, what is this measurement? Well, we know we go from the bottom of the meniscus, so it's about there. Well, what is that? Some people would say it's 4.4. Some people would say it's 4.5. Some people would say it's 4.6. That's sort of up to you. But the thing to remember is that both of those numbers are going to be significant. Because, and this is I know it sounds a little weird, there is always one sort of estimate in any significant figure. So like when we measure 4.4, we know it's 4. We know it's more than 4 and it's less than 5. So this is clearly significant. But this is significant too, because it's your estimate as to what that in between 4 and 5 is. That's also significant digit. So you would get 2 sig figs from this. So same thing with reading temperature. When you're reading a thermometer, you're not going to get, unless you're using a digital thermometer, it's not going to be extremely accurate. You're going to have to interpret the distance in between the degrees and then make a judgment on your own. It's like what actually the temperature is. So you're going to be doing this a lot during this particular experiment. So these are be random errors. There's really nothing you can do about these. You can try and minimize them. How would you minimize that error of reading the meniscus? So here's our graduated cylinder. There's the meniscus. How do we minimize one way to minimize the error of reading that? Anyone have any ideas?
You could find the median.
Apply the median.
No, like average them, like.
Yeah, you measure it a couple of times.
Mm-hmm.
Measure it a couple. In fact, that's something we'll be doing tonight. Measure it a couple of times and take the average. What's the most accurate way to look at that?
to
But-
read the label, the numbers on them?
Yeah, I'm just going to go grab it. It's right over there. I'll be right back. I'll give you a good idea what I'm talking about. Okay, so here's my graduated cylinder, and you can see it's got the little check marks on it. So what's the best way to look at it? Do I look at it from above? So if I have it like this, do I look at it from above? Do I look at it from below? What do I need to do when I'm looking at the meniscus in here?
Eye level?
High level.
Exactly. I've got to look, I got to get down to whatever level that is. So if it's around 8, I have to put my eyes right at 8 and then look directly at it. Because if I look above, it's going to look like it's smaller than it really is. And if I look from below, it's going to look larger than it actually is. So that's one way to reduce the error for that particular measurement. So our data needs to reflect the reliability and the precision of whatever measurements we're doing. So this is where significant digits comes in. So for example, the balance you're going to be using gives mass to the nearest hundredth of a gram or centigram. Or I think some of them might be milligrams. I'm not sure. So basically what that means is that if you measure 100.0000 grams, that means that all these numbers are significant. Because if it wasn't, you wouldn't be getting this particular. It means it can measure these things within 100th of a gram. So you include all of those numbers when you're doing your measurements and figuring out your errors. Now, who's taken statistics before?
Me.
I recommend taking statistics, man. I mean, it's still like, 35 years on, it's still probably the best class I ever took in college. Because I mean, I still use it every day in thinking about things. So I hardly recommend taking statistics, particularly because of the sort of science that we're doing these days. We're doing these like vast population based science studies with huge amounts of data that we weren't able to do before. We just didn't have the instrumentation. We didn't have the computers. We didn't have a lot of this stuff. So now statisticians make big money. Statisticians make more than scientists do, which is, a sad thing, but there you go. So these are some of the things that you're going to need to become familiar with. So standard errors, average value, standard deviation. Everyone's probably heard of standard deviation, but you may not know how to calculate it. If you have a scientific calculator, it will do the calculation for you, which is obviously the best way to do it, but I want to show you exactly what that means. And then there's relative standard deviation, which is just basically a way of saying how accurate your answer is. If you say it's, if your answer is like plus or minus 1.6, I don't know what that means. But if you say it's plus or minus 5.5%, then, oh, okay. Then you have an idea of how accurate your answers were. And then we'll talk a little bit about relative error. So this is just basically going back and giving you an idea of the difference between precise and accuracy. So all of these things, these are like if you're taking lots and lots and lots of measurements, and then you would plot what those measurements are. If they were very precise, you get a very narrow set of numbers, obviously. The more numbers you would get within a very small window, the more accurate it is. And you would hope that the mean or the average of all of your numbers would be very close to what the real value is. So in number A here, box A, we have both precision and accuracy, which is the best of both worlds.
Professor,
Yes.
when are you meaning for us to be looking at something that you're looking at? Because we can't see your screen.
You're not
Or I
seeing it
can't.
anymore?
I don't. Maybe it's just me.
I can see it.
I can see
Yeah,
it.
I can see it too.
Huh,
Okay, this is me.
weird. Yeah, just try
Okay,
futzing around with the
okay.
with the zoom. Maybe like a full window
Yeah.
might help. So in B, you're getting your precision because all of your data points are falling within a very narrow window, but they're off. This would be an example of a systematic error. Systematic error, where you're getting really, really precise numbers. You're getting the same result over and over and over again, but they're all wrong. So that's not great, unless you can figure out how to fix it afterwards. And then down here, number C, that is basically what I showed you with the three numbers, 90, 101, and 109 for the boiling point of water. They're sort of all over the place, but if you take the average, it's actually really close to the real value. So A and C are really what we're looking for. D is the worst of all, meaning we got crappy data and it's wrong. So that's like nobody wants that. So how broad this curve is, or how much spread there is in your data, really depends on what kind of instruments you're using. And I think you'll find that out tonight when we're measuring the volume of water using one of these, using a flask, using a big beaker. You'll find that certain things are designed specifically for accuracy and certain things aren't. Like basically a beaker is not meant to be used to measure something, and that should be made abundantly clear, probably from your data. So average, I think everyone knows how to compute average, or mean. It's the same, means the same thing, and that is represented by just having a dash over the top. So each one of these is particular measurements, and then the mean or the average is just all of them divided by the number of measurements you've done. I think that's pretty clear. But deviation basically says how much is your answer changing each time. Now this isn't telling us how much it's deviating from the actual answer, because we can figure out what our deviation is without even knowing what the actual number is. So here, basically, here's our mean again, or our average, and then the deviation is like how much does it change each time from that average. So what we would like the deviation to be small. Obviously, if you get small amount of deviation, it means it's precise. So you can basically say how much each particular number, each particular measurement differs from the average. And this is basically how we know how to throw away outliers. So if we find out that, like, we've done 4 measurements, 3 of them are within 1% of each other, and one of them is 25% different, obviously something's hinky with this one, and we just toss it out. But we make sure that we know what we can justify it by showing what the deviation is of that one first. We don't just go throwing data away because we don't like the looks of it. Although I've been tempted to plenty of times, believe me. So standard deviation basically just gives you an indication of how wide this curve is. And you've seen, so if this is a curve of all the measurements we've done, we want this to be as narrow as possible. We want those, supermodel deviation. We want it to be as, just sickeningly thin. So it's basically just a measure of how wide that curve is. And standard deviation is given this particular symbol, sigma, for standard deviation. So that we want it to be as small as we possibly can get. And this is how we dictate this. Now, there's a lot here. Don't worry about having to do this. Hopefully, if you have a scientific calculator, it will do this for you automatically. Or you can go online and put your data in, and it'll spit out the standard deviation. But I just basically want to show you how it works. So you take the mean, you take the deviation, and you basically measure, you add all the deviations together. So all of them together, and then divide them by the number of measurements you've done, -1. And then just take the square root of that. And so that gives you an idea of how, again, how wide that band is, that group of data. So this is probably one of the things that is most understood or recognized and reported is what's your standard deviation, particularly if you do lots and lots and lots of measurements. If you're doing thousands of measurements, then you definitely give standard deviation. If you're only doing like 3 or 4, generally just deviation or accuracy is enough. So I just wanted to give you an idea of how that looks. So basically, the standard deviation, it gives you, when you say plus or minus, and you probably heard this before, like when some idiot is talking about a poll on TV or the radio or something saying, 44% of people think that, Joe Biden should be, shot into the sun or something. Plus or minus 5%. What they're talking about, that's the standard deviation. So the 44 would be here, and there would be 5% on this side and 5% on this side. And it gives you an idea of how accurate this number is. So you probably hear that because polls are reported all the time, but nobody pays attention to what this is. That's the standard deviation. So if you get something like, 40 plus or minus 10, that's a meaningless number. That means it's anything, anywhere between 30 to 50%. That number could be anywhere. So the more people you interview, the more measurements you take, the smaller and smaller that standard deviation gets. So relative standard deviation just basically turns it into a percentage. That's all that is. So you take the standard deviation, you divide it by the mean and multiply it by 100. And that gives you an idea of relatively how accurate something is. So if you say my measurement of the temperature, the melting temperature of iron or whatever it is like 1735 degrees plus or minus 2%. That's your relative standard deviation. All right. Relative error. Now that once you've if you can figure out what the accepted value or the proper value is, for instance, we know what the mass of water should be. The mass of water should be 1 gram per milliliter. That's like pretty much. We'll look up what the density is at the temperature of wherever it is you are. This room, the temperature will vary and the density of water will vary according to the temperature. So we'll look that up. So basically we can calculate what we think the density of water is. And so our relative error would be what we've measured. This would be our average minus what the actual value is. So divided by actual. So we want our relative error to be small. Of course, if we're measuring something that no one's ever measured before, we don't know what the relative error is. We can only say what the relative variation in our data is. But when we're measuring something like this, like tonight, we're going to be measuring the volume of water and then figuring out what the mass of it is on a scale. That will tell us precisely what the volume is based on the mass and the density. So we know what our answer should be, and then we can compare it to what we measured it as. That would be a relative error. And then percent error is just your relative error times 100. So that's fairly straightforward. So here's our first experiment we're going to be doing. So now you don't have to do the lab tonight. You can do it later. But if you are going to do it tonight, you know, have your lab book ready. Hopefully you've got something to take notes on. Have a clean workspace. Here I am with my drink, but I wasn't going to be doing it. I'm going to be doing the lab in a little slightly different place. So yeah, I may look like a bit of a hypocrite having some tea, but it'll be in a different part of the room. Tell everyone in the house about your experiment. Oh my God, I'm going to be working with water. So run for your lives. It's going to be very, very dangerous. Tonight, obviously, you know, not too many safety concerns for tonight. I think the worst thing that could happen is you could spill some water on the floor and someone could slip on it. That's pretty much about it for tonight. There'll be more safety concerns in the future. So if everyone has their kit, these are all the things that we're going to be using tonight. So we have our cute little graduated cylinder. So this is 10 mils. And one of the things it says on it, if you look, I don't know if you notice at the very top, it says two things. It says TD and TC. Anybody know what those mean? So right on the very top, it says TD, TC. Anyone want to take a guess at what that means? I'll give you a hint. The T stands for 2. So if we're pouring water in here, what do we expect it to do?
Fill the container.
Contain.
Is it to contain?
That's what the C stands for. Excellent. Yeah, it says it will. So if it says 10, if you have the meniscus is right on 10, it basically says it will contain 10. And if you look at it, it's plus or minus 0.2 mils. So that is it says right here at the top. I don't know if you can read that. It says 10 plus or minus 0.2. So that is basically what they have measured as the precision in this particular instrument. What do you think the D stands for? Because once it's contained something, what do you do with it? So I measure, like I'm doing an experiment, I want 8.8 mils of water. I put my 8.8 mils of water in here. So now I know it's containing 8.8 mils of water, but then what do I want to do with that 8.8 mils of water? Am I just going to leave it there, or am I going to do something with it?
Drop. I don't know. Dump.
Drop. That's a good guess. You're very close.
Drain.
Drain. That's good too. I think someone had it.
Deliver.
Deliver.
Oh.
Perfect. Yes, deliver. So this is one of the few scientific instruments that's both designed to contain and deliver. Some things are designed to contain and other things are designed to deliver. This is designed to do both. And so basically what it tells us is that if it has 10 plus or minus 0.2, when you empty it out, you will have delivered that same volume. And so it helps actually that it's plastic. Glass tends to hold on to water through surface tension. Plastic, you don't have that as much of a problem with that, because one is hydrophilic and one is hydrophobic, and we'll learn about that later. So we have a 10 mil cylinder, we have a 50 mil cylinder, and we'll see what the error is with that one. We have our balance. Hopefully everyone has their balance or their scale. a 25 mil Erlenmeyer flask. Now, what does that look like? Anyone want to hold up the Erlenmeyer flask to the camera? Let me see. Caitlin's looking. Oh, she's got the, you haven't even taken it out of the box yet. Oh, come on. Rachel, you got it in front of you? There it is. Wait a minute, what is that?
I don't know if this is it. I just took it out of the wrapping.
I can't even think. Oh, yes, that's it.
I'm gonna
Yeah,
open
so
it.
it looks like this.
It's little, yeah.
Yeah, it looks like that. Now that is basically designed to contain. That is not designed to deliver. That's designed to hold something, to hold a certain, because you do basically what the flask is for doing reactions in. So you pour things in it and then, you know, magic happens. And you're supposed to have it inside the flask. You can heat it and you can, you know, you can chill it and all sorts of different things. So it is not designed to transfer liquids from one place to another. So it is not going to be accurate. Not nearly as accurate as a graduated cylinder. And we've got a beaker, big beaker. What's the difference between a beaker and a flask? Anyone give me an idea what the difference between a beaker and a flask is? Everyone gets quiet. Fatima, what do you think? Beaker and a flask, what do you think the difference is?
Could it be the shape of it?
Definitely the shape. So what's different about the shape?
I don't know.
So if this is basically what a beaker looks like, and this is what a flask looks like. So what's the difference?
The volume?
It's about the top. What's different about the top?
One's bigger than the other.
Yeah, big time. Basically, a beaker is the same size on the top and the bottom. Now, a flask will narrow. It is a narrow opening. And that's because usually, like I said, we do reactions in flasks. And we don't want them, you know, flying up and spilling all over the place. So the top of them is very narrow. So if there is like bubbling and everything, it's sort of contained within it. Beakers is basically used for just doing things where we don't expect a lot of splashing to take place. So you can do mixing in a beaker as long as it's not too dramatic, but we generally don't do like hardcore reactions in a beaker. And we'll use them if we want to measure something, but we don't need it very accurate. Like, you know, if you want like, oh, about half a liter of water, we'll just, you know, fill up a beaker to, you know, where it says 500 mils, and that's close enough. If we need precisely 500 milliliters, we would get ourselves a 500 milliliter graduated cylinder and get it to a precise place. So we'll need a thermometer because, like I said, the density of water is going to be different depending on whether you're at 20 degrees or 25 degrees, or you have like a lot of old people in your house and they like it really, really, really hot, the density will be different. You should have a marker. It can be a wax marker, it could be the Sharpie. It doesn't really matter as long as you can mark on the plastic. And then a couple of plastic cups. So you should have some distilled water. If not distilled water, filtered water at least. If you're just using tap water, that's fine. Make a note of it in your report because that will be a source of error. Because what's the difference between distilled water and tap water?
Distilled water is filtered.
Not just filtered.
Processed. I don't know. Never mind.
What does distilled mean? That's a good question. What does distilled mean? If I distill something, what does that mean?
Is the pH different?
Yeah, I would say the pH is probably slightly different because of what's in distilled water and what isn't. So the pH could be a little bit different. But what does it mean to distill something? If I distill something, what does that even mean?
To
Like if
purify
I,
it
right? Yes. How? How am I doing that?
by boiling it, maybe.
There you go. So if I'm making moonshine, they say a moonshiner's got to still, right? That's what. So that's what they do with the stills. They make alcohol using yeast and corn or whatever it is they got, but that's at a very low concentration. I think the highest concentration you can get is around 15% or so before the yeast go. That's too much ethanol and they croak. But you can't sell 15% moonshine. You'll get run out of business. How do you get it up to, 70, 80%? You boil it, and then what? That's only half the battle. What else do you have to do? So I've got my pot, and
You let it evaporate. I don't.
so you're boiling it. You're turning it into. So I'm boiling my moonshine. I'm boiling my mash, right? I'm boiling it. So the ethanol is boiling off. It's turning into a gas or a vapor. But I'm not done. I can't just sell vapor. No, nobody wants vapor. What am I going to do with all this vapor?
You have to collect.
Yes, exactly. I cool it. And when you cool it, what happens?
Condensation.
Exactly. So first you have evaporation, and that is changing a liquid to a gas. And then you have condensation, which is changing that gas back to a liquid. And so basically what you do is you keep repeating this process over and over. So I start with, let's say, 15% ethanol, and I boil it, and then I cool down the gas, and then I find I've probably got about 30% ethanol now, because there's always going to be some water carried over. And then I take that 30% and I distill it again. Now I've got 40%, and then I do it again, and now I got 50%, and I keep distilling it more and more. And every time I do it, I leave more of the water behind. And so that's how you do. So distilled water basically is just water, tap water that you've boiled, and you leave all of the salt and ions and other things behind. And basically you're left with more or less pure water without any salts or buffers or anything else. So it should be pure water. It's not going to be exactly pure, but it's going to be like 99.99% pure. So water out of the tap is going to have salt. It's going to have sodium. It's going to have potassium. It's going to have calcium. It's going to have nitrates and phosphates and all those sort of things. It's going to have fluoride, all that stuff in there. So the density of it will be slightly different. It won't be radically different, but it'll be slightly different than pure water. So if you are using tap water, make sure you make a note of that, because that will be a source of error in your experiment.
Are we going to need? Are we going to be using distilled?
We're going to be using distilled water again?
Yeah.
Yes. Yeah, pretty much all the experiments, any experiments using water, you want to use distilled water.
Okay.
Because there may be some experiments we do with when you're adding ions. So you're adding metal ions to water, and if there's already other ions in there, they may precipitate, and we don't want that to happen. So you can just get a jug of it at the grocery store for like next to nothing. So it's not that big a deal. If you can't get it, you can't get it. That's if you have filtered, we'll just go with that. I mean, that's at least better than just right out of the tap. So, but if you can't get your hands on some, I understand. But yeah, you don't want to use,
Maybe not tonight.
yeah, maybe not tonight. Yeah, but don't use like spring water or stuff like that. That stuff has a ton of ions in it. Some of it which makes the water really, really good. Like I like Fiji water, even though it's evil as hell. It's still really, really good because it has all kinds of silicates in it. It has that special, really smooth mouthfeel because basically it has a ton of silicate ions in it, which is just num, 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 num. But it's not something you want for doing experiments. Okay.
How much
So-
water do we need for today's experiment?
Oh, not much, like maybe 100 mils total. I just like filled up a glass. That should be plenty.
Okay.
Yeah, so obviously since we're just using water, don't have to worry about cleanup. So here's what the lab basically entails. So we have our 2 cups, and we're going to mark on them 1 and 2. So the very first thing will be working out how reliable is the data we get from your balance. So that's this really straightforward experiment. All you're going to do basically is measure the mass of each cup 4 times. So you're just going to take 4 measurements of mass of each one. So your balance is going to look like that, or mine's from a different kit. It looks slightly different. But you see that it has 3 buttons here. It has an on-off. It has a mode, which is basically, do you want grams or ounces or, grains or whatever. And this last one is called tare. What does that mean? The tare button. Oop. Tare. What's tare? Anyone tell me what that means?
Does it mean to reset it?
Oh, Ruby, you're having a hard time with your internet connection tonight, I think.
Yeah.
Yeah.
Oh, now is it not working good
Well, now you
or-
sound fine, but sometimes you sound like you're being stretched apart, like you're falling into a black hole or something.
Oh my God! And now I'm on my phone, so there shouldn't be any issue at all.
Yeah,
But,
that sounds much better. Yeah, basically it means
Okay.
reset. It means reset. So we use this a lot. Like if you put your cup on it, it will give you the mass of the cup. Okay, but what if you want to pour, let's say, what if you want to put 10 grams of sodium chloride or something into that cup? Well, all you do is press the tare button and then it goes back to 0. Basically, what it's done is taken the mass of the cup and then subtracted it. So when you hit tare, it then goes back to 0. And now you're just measuring the mass of the salt you're putting in there rather than the cup. It comes in super, super handy. I use it all the time. I roast coffee beans at home. And so I put, a big beaker down and then I pour my coffee beans in it, but I tare it first. So then I don't have to do math in my head because math is hard. So that's what that's what the tare button is. Comes in super, super handy. So basically, you should have a table in your report. I think it's already set up, where you get the mass of the first plastic cup, mass of the second plastic cup, and you get the average mass. One thing I really want to point out to you is that when you have a data table like this, it is essential that you have units in it. Because if you have mass of plastic cup and then you write down 10.76, that is a meaningless number. 10.76 what? Grams, pounds, kilos, fish? I don't know what that is. So you always have either put, it's easier just to put the math, just to put the units at the top. That way you don't have to keep putting it in every time. But you have to have a unit in there, because I will scold and point my finger and give you marks off if you do that. So just saying, make a note of the unit. So here's the average, you know how to do that. And then determine the uncertainty in in the lab balance. So what's the average mass? And then minus whatever the particular measurement was. So let's say your first measurement was, let's say the average is 10.01. Your first measurement was 10.02. The second one was 9.98. You then just basically subtract each one of these from the average and give the deviation. So there should be a pretty small, I would imagine you're gonna have a pretty small deviation. I think they are rated to plus or minus 0.01 grams. So hopefully your deviation should be somewhere around there. Fingers crossed. If there are a lot more, let me know, because there's either a problem with the balance itself, or maybe something else is wrong. But you should have a pretty low deviation. Then we're going to look at the different glassware. So these are the three things we're going to be, or four things we're going to be using to measure. So this one is the 10 mil graduated cylinder. This is our 50 mil graduated cylinder. This one's our beaker. You can tell it's a beaker because it's big at the top, big at the bottom. And this one's our cutesy wootsy little 25 mil Erlenmeyer flask, invented by someone named Erlenmeyer. Frighteningly enough, yes. So, and we're going to be using distilled water for this. So basically what this is going to do is give you an idea of which one of those is basically the best at measuring volumes. And it probably won't be terribly shocking to know which one is most accurate, which one isn't. So what we want you to do is put 7 mils of water in the 10 mil graduated cylinder, 24 mils of water in the 50, try and get 17 mils of water in the 25. Now, remember, you're going to be way off on this. Don't feel bad and like, man, how the hell do I find 17 mils? That's the whole point. It's like, it's going to be really, really hard to try and figure out what 17 mils is in a 25 mil Erlenmeyer flask where there really aren't any directions as to like where's 17 on this thing. You basically have to estimate it for yourself. And then for the 250 mil beaker, estimate how much is 35. And how are we going to figure out how close you are to the volume? How are we going to figure out the volume? So these are going to be what you're attempting to put the volume in. How are we going to know what the actual volume is? Can someone tell me how you're going to know the actual volume? How do we figure that out? Because we need an answer, right? We need to know what the answer is. We need to know what the actual volume is. How are we going to calculate the actual volume?
You can use a density formula.
What do we use the density for? What's the density going to do for us?
Like the DMV formula thing.
The Department of Motor Vehicles formula? I don't know what that is.
Mass over volume.
Right, so density equals to mass over volume. So basically, it's the relationship between mass and volume. So if we want to know what the volume is, and we don't know what it is, how do we figure out what it is using D equals M over V? What are we going to measure to tell us what the volume is? Because we can't measure the volume directly. How are we going to measure it?
Use the mass.
Exactly. We're going to use our balances. We're going to determine what the mass is. So we will know two things. We will know what the mass is. We're going to measure the mass. The mass will be measured. The density will be determined from the temperature. So the density will be a known thing. The mass will be a measured thing. So if I take a measured thing and a known thing, I'm going to get a measured thing out of it. So basically, that's how we're going to measure the volume. by measuring the mass and then converting it to volume using this formula here. Right, using our Department of Motor Vehicles formula. Excellent. So we'll measure the weight of each one of these. Actually, I should say mass. What's the difference between weight and mass? Can someone tell me that?
One of them is compactedness, right? Mass is
Compactedness. Wow, I like that word. Isn't
Or-
that density?
Oh wait, no. Yeah, never mind. I guess never mind. I thought I had it.
This level,
What is it?
like the surface area.
Surface area. Nope.
It's the unit of measurement.
They're both units of measurement, though.
Right, but they're different. Different. You use a different unit to measure with.
No, they're
The
both
way you
grams.
measure is different.
Nope, both grams, kilograms, pounds. I'll put it this way: if you go into space, what changes, your weight or your mass?
Your mass, your weight.
Your weight. Yes, your weight changes. Does your mass change?
No.
No. Yeah, you might like to think, I mean, I'd certainly like to think so. You know, I'd like to go to the moon and weigh 1/6 that I do here. That'd be awesome. Unfortunately, my mass is going to be exactly the same. So the difference between weight and mass is that weight varies depending on gravity, and mass does not. So your mass is your mass is your mass, depending whether you're on Jupiter or whether you're here, whether you're on the moon or whether you're on Mars or whether you're, 50,000 feet below the sea. Your mass doesn't change. So we'd like to say we measure mass because weight can vary. Mass does not. So that's why we measure mass. So what are some of the other things here? So we'll record the mass of each one, put them in the table. We'll add the volume of distilled water as we can. And one thing I would recommend, and I'll show you when I move over the table, you should take out a transfer pipette. Now, you may not know what a transfer pipette is. It's the one with the little bulb on it. There's a little bulb at the top. That will be very helpful for adding precise volumes to these things, because it's really tough to just pour in from a big glass and get exactly 7 mils. You're going to want to add drop by drop. So I'll show you what the transfer pipette is. That wasn't included. So you record the values. So you get a lower limit, especially with your flask. With your Erlenmeyer flask. It's gonna be really hard to figure out what 17 is, but give what you think is the lowest volume it could be and what's the highest volume it could be. And you measure those two. Then you measure the mass of the filled glassware. Or you could also just hit tare and measure it before and after. So, and then record what the mass is of just the water. And then we're going to take that mass of water and convert it to a volume, okay? All right. So this is what that should look like. So you should have a table or something that looks somewhat like this. So what's the mass of it empty? What's the mass of it filled? What's the mass of the water? What do you think is the smallest volume it could be? What's the highest volume it could be? That gives you some amount of the uncertainty there. And then we'll figure out what the volumes are based on the mass. So this is where we figure out the accuracy is by using your thermometer, getting the temperature of the room you're working in, the data from here. These are the masses. of the glassware and the volumes you figured out. And then table 2. So I will show you what table 2 is. So hopefully everyone has their experimental procedure from the company. So there is a procedure that comes with it. Hopefully you can see it. Does this look familiar? Can you see the procedure from Carolina here? Can you see it on your screen?
Yeah.
Yeah.
Okay, good. So at the bottom, almost at the end, they have table 2. So at table 2, they give all the densities of water at different temperatures. And you can see, they don't vary much, but they do vary some. And they go from 18 degrees C all the way out to 28. So it started, what happened there? Freezing up. Right, 27, there's 27. So, and the way it works is that each column is 0.1 degrees. So this one would be 18.1, 18.2, 18.3, and so on. So let's say you measure the temperature in your room and it's 20.5 degrees Celsius. So you would go 20, 1, 2, 3, 4, 5. So that will be the density of pure water at 20.5 degrees. And then this would be, that would be 1, 2, 3, 4, 5. Right, so 0.9981. So then we use that to convert the mass of the water in our container to a unit of volume. And that way we can figure out what our error is. Okay, so any questions before we get started?
Yeah, you lost me about 5 minutes ago.
Oh dear. With what part? I can't hear you.
This table.
Oh, the table. The table is
this table.
The table is the density of water. So let me just go down here. This is what the water density is at different temperatures. So H2O density in grams over milliliters. So we pretty much always say that the density of water is like around 1 gram per mil. Well, it is. It's around 1 gram per mil, but it isn't exactly 1 gram per mil. So when you measure the temperature of the room you're in, wherever you're doing your experiment, you go over here to the side, and let's say it's 22.6. So we'll go to 22 degrees, and we'll go 1, 2, 3, 4, 5, 6. So at 22.6 degrees, the density of water is 0.9976 grams per mil. So if we measure our mass of water, we can then convert it to milliliters of water.
I don't understand. Maybe it's just because I didn't review this chapter well enough, but I understand the part up until you start counting over to the right, however many places you're going. How do you know to do that?
Oh, because it says right here.
And how do you know how many?
0.1, 0.2, 0.3, 0.4, 0.5, 6,
Where-
7, 8.
Okay, but what's that?
So whatever temperature of the room we're in. So for instance,
Yeah.
if it's 22.6 degrees Celsius,
Right.
we go down to 22 and we go over 6. So we
And
come
why
to,
do we go over 6?
because the density is going to be different depending whether it's 22.1, 22.2, 3, 4, 5. Even small changes in temperature change the density slightly.
Okay. Oh, okay. All right. Thanks.
And you'll notice that when it's colder, the density is higher. So like at 18.0 degrees, it's 0.9986. At 26, almost 27 degrees, it's 9965. That may not seem like a big difference, but that's a pretty big difference. It's like a, that's a almost 1% or 0.2% difference. So that will make a specific, that's an error that you don't need to have in your experiment. This is a classic example of a systematic error we can correct for. Just by knowing the temperature, we can correct an error like this and eliminate it. And whenever you do an experiment, you want to eliminate as many errors as you possibly can. And this is one way of doing that. Instead of just using 1 gram per mil, we're going to use the actual density. So any other questions before we well, I'll sort of get you guys started, and if you have some questions, and then we'll call it a night. So any questions before we start?
For the lab report, we're turning in the PDF that he put under lab report, right?
Yeah.
It has to be handwritten.
All right.
Oh, you can't type on it?
I don't believe so, no.
That's a drag. Okay. I'll find out if you can, because obviously that would be easier, I think.
I think that he
Printed.
wants us to do that to make sure that like it's us that's doing the work, maybe.
Yeah, could be. But yeah, everyone knows how to like just take a picture and can convert it to a PDF with your phone, or can everyone do that?
So we have to print out the pages?
Looks
Yes,
that way.
yes, that's right.
I'll find out for
You
sure.
can
but-
transfer it to a Google Doc. It'll let you type on it.
I think it lets you type.
Yeah, I just so you guys know, there are explicit directions and instructions from
from John
gosh,
Saunders.
I'm drawing a blank on his name, but on how he wants us to do these labs, and it says to print them out, to write very neatly, handwritten, and then to upload the PDF in one PDF. So you'll have multiple pages, but he wants one PDF uploaded, and that's how he wants them submitted.
Okay.
So I don't remember exactly where I got the instructions.
Yeah, I'll review that too.
But
I'll
those were
review
the
it as well.
instructions.
Because yeah, some people might not have printers.
I don't have
I would think a lot of people don't have printers, right? So yeah, so we may have to have some. I may have to find out, how we can get some flexibility in that. Because yeah, printers, that's kind of like that's at least a 10-year-old invention at this point.
Well, I
Right?
mean, you could use your phone. I don't like it though, but you can use your phone to take a picture and convert it to PDF. But sometimes if you don't write dark enough, it just gets annoying having to retake it over and over again.
Yeah. Yeah. Well, yeah, that's the way I've been doing it. Yeah, but I have a printer, so I print it out and then take a picture. So yeah, it's kind of tough if you can't print it out. So I'll find that out if there's more than one way to do it. Because yeah, if you don't have a printer, there's basically you can't do it that way. I don't think we can make you go buy a printer. So I'll find out from John tomorrow. Okay. So anything else before we get started?
Just to clarify,
Sure.
this table, the temperature that we're using, is this the temperature of the room, not the water, right?
Well, actually, you put it right in the water. That's a really good point. If you've had that water in the room for like at least half an hour or so, that actually would be sort of more accurate, because then you wouldn't be getting like breezes from the window or whatever else. That's an excellent point. That's what I'm going to do. Actually, that's a really good point. Is put my thermometer in the water, and then measure the temperature there.
So if our water's not like room temperature, we shouldn't.
No, like if you just got it out of the tap, or if you had your distilled water in the fridge, then don't do it that way. But if it's been sitting out for like at least 30 minutes, it should now reflect what the temperature of the room is.
So just like keep our thermometer in the room that we're in and just.
Yeah.
use the reading of that.
Yeah, just have it on the desk wherever it is you're reading. Just have a look at it, and you might want to check it a couple times. It may change. And the other thing, like when you're reading it, obviously you don't want to hold it with your thumb and then look at it, right?
Yeah.
So yeah, sort of hold it by the top so you don't add any of your own body heat to it. Anyway, I'm gonna, yes, go ahead.
Oh, one quick question. To find the lab report, it's under like your information, and then it's under lab manual, and then it's under experiment 1, measurements and uncertainty. Is that
The
like
lab manual? The lab manual is this document right here.
Okay.
It's basically this. It gives you the rundown of like exactly what to do, all the tables, and that sort of thing.
What am I turning in? So like the lab report templates underneath that lab manual button.
All right, let me see if I can find it. Where does everyone else found their template?
There's 2 documents that I have so there's 2 documents. I don't know exactly where I got them from though, but I'll let's see, I can send them.
It's in either a doc or a PDF format.
Oh, okay.
The lab report, yeah.
Okay, so it's just on that main page.
It's where the lab manual is, like for each experiment, like it should be on there.
Okay, thank you.
Yeah, so under my tab, it's the 3rd tab over. So there's the instructor information, Zoom info and recordings, and then there's lab manual, and you just go down. So lab report template, and you can either get a Word document or a PDF. So Word document, that'd be much easier to edit, I would think. PDFs are a pain in the tuchus to try and edit. But if you're just going to print it out and draw on it, then it really doesn't matter which one. Okay. So I am going to move and give you an idea of like how we got this thing set up over here. All right.
Does anyone know where or which bag the thermometer is in?
I took everything out already. I can't remember.
I think it's in that same bag.
I think it's in the big bag.
It's in this thing.
There's one big bag with a lot of stuff in it, I think. Okay.
Bag.
Oh, this will be fun. All right, so I've got my thermometer here. So you don't have to worry, there's no mercury in here. These are, most likely this is a alcohol thermometer with some red dye in it. So what's suggested, which was an excellent idea, just pop it right in the water. I've got my glass of distilled water here. I'm gonna pop it in there and let it sit for a couple minutes. So this is the transfer pipette I was talking about. So you can see it's got a bulb on the top, and when you squeeze it, you suck water in, and then let it out. Squeeze it, open it, squeeze it again. So this thing is really good for if you just want to do like drop by drop additions of water. You'd use something like this. Okay, so basically you could pour until you, let's say I've got my 50 ml container here, and I think it was 35 mils of water, I think it was, something like that. So you can pour it up to 30 pretty quickly from the glass or whatever container you have, and then to get it right up to 35, just add drop by drop with your transfer pipette. And you should have about 5 or 6 of these, maybe even more in there. These are incredibly handy. And they do have tiny little marks on them to tell you that it's a mil, but these things are not accurate at all. So basically we don't use these to transfer like extremely accurate volumes of water, but they're great for just transferring from one place to another without making a big mess. So I'm going to check my temperature, and damn, it's kind of cold in here. I've got 15. Eesh. Obviously, out in the garage is not a great place to be doing this. So yeah, 15 degrees for me. I'm probably going to have to look up the density because I think that table didn't even start till like 18 degrees. So if your temperature is either above or below whatever was in that table, I think it went from 18 to 27 degrees. If it's either below 18 or above 27, just look it up. Just Google density of water, 27.3 degrees C. It'll spit it out for you. All right. Here are two cups. So 1 and 2. So I've already marked them with the wax pen. Well, I've marked this one anyway. So 1, and I'll mark on the other one 2. There we go. So everyone has a scale, right? I'm assuming. The first part of the experiment will just be insanely easy. So you can go through that one pretty quickly. I think my scales and my balance is going to look slightly different than yours. So I've got this black one here. Everyone else has the silver colored one.
Yeah.
Okay. But they're all going to work pretty much the same.
Professor, I don't think I got a thermometer.
You don't have a thermometer? Oh dear. Okay.
It's not in that thingy. This thing.
It comes in a plastic
Check the
plastic
small
container
bag.
like this. I didn't think I had one either, but it's in
Check
there.
the bag with the pipette. 'Cause I think that's where I
Yeah.
found mine.
Pretty much everything's in that bag. They stuffed everything in there. It's pretty amazing.
Oh, I got it. Thank you.
Got
Thank
it?
you.
Yeah. Because these things are really small. It's really easy to miss them, especially this balance. I didn't think I had one, and then it's so little. So you'll find that the balance won't even work until it's on a flat surface. It's really critical that you have a flat surface. If it's tipped to one side or another, you're not going to get a very accurate measurement. And the other thing, if there's a breeze, or if you're like by a window, or just even people just walking by, notice if you blow on it, it'll change. So it's really critical when you're taking the mass of something. Generally, when we're in the lab and we want to get an accurate mass of something, we have it inside of a case that we can close, because we don't want just air currents in the lab, just like from the AC or whatever, will blow air onto the balance and change the mass. So when you're measuring the mass of something, you definitely don't want to have it, you don't want it moving. You don't want people moving past it. And you don't want to be too close to it and like blowing on it. So the mass of mine, so what are you guys getting for a mass of your plastic container? Your first plastic cup? I'm getting around 10.17 grams. Does that sound about right?
I got 10.02.
Okay. Yeah, I'm thinking they're all going to be around 10. But man, the more I talk, the more the mass changes. So you may want to wait for a minute. Oh man, it's gone from 10.17 to 10.21. It's because I'm flapping my gums here. Yeah, so sort of get away from it and let it sit for a minute. And then measure. Yeah, it's gone back to 10.18.
Well, I'm getting 10.2, like a 10.2 in a 10.20s. Is that too?
10, so if you have 10.20, all of those numbers are significant, right? Because the 0 is past the decimal place. That 0 is there for a reason. It means it's not 10.21 and it ain't 10.19. It's 10.20. That 0 is important. Man, this thing is changing all over the place. So yeah, I think it's really important to, you don't want it to vibrate. That might be a problem. Because if you just tap the table, it changes. And that's some of your error is going to be from that. There's really nothing you can do about it. So what I would do is just sort of wait for the mass to stabilize and then take the reading. Mine seems to have stabilized at 10.16, and now it's changed. As soon as I said that, it changed again. Yeah. So again, this is part of doing science. You know, we're doing science in our house. It's not like we're doing it, you know, in a rarefied environment. So these are the things that are going to change. So you take 4 measurements, and when you take it off, make sure you hit 0 again, because it might not go back to 0. It might be a little bit more or a little bit less. Make sure you hit 0 or tear when you take the cup off, because every time it's got to be reset to exactly 0.00. Okay, because right now mine's saying negative 0.05. Well, that's no good. So I hit tear, it goes back to 0. And then I'll check it again, see what I get this time. And again, mine's flux. Everyone else see the little fluctuations? Everyone's getting that too?
Yeah.
It's not just me with my big nose breathing on it.
I think my table's also like kind of like this.
Mm-hmm. Yep.
So
yep, that's an issue. See, that's the perfect thing to put in your report, because we don't just, you know, when you do an experiment, you don't just, you know, you look at the mass, you write that down. If you see something that might affect the experiment, you write it down. You make you note these things. Like for instance, like I remember I was doing a lab with a class a couple of years ago, and someone noticed that, you know, the flame they were burning was a bright orange rather than yellow. They said, "Should I mention that?" Yes, you should definitely mention that. That could have real relevance for your experiment. It means that there's something in the flame that shouldn't be there. So that could be changing, you know, the outcome of your experiment.
My numbers were kind of low. I got 9.93.
Everyone's cup. I mean, these things aren't going to be made to extreme tolerances. So I'm kind of curious to see, like, you know, what if we look at everybody, how different they're going to be, you know, because.
So we're doing it five times?
4 times. 4 times. Yeah, and I think we'll find that these are probably going to be within about maybe 1 or 2% tolerances. So even like 2% would be, you know, 0.2 grams. Yeah. That's a big difference, you know.
I'm just a little confused. So I should just ignore the 5th line on my.
Oh, do you have 5 there?
Yes. Yes,
okay.
I do.
Yeah, then just do 5 then. Yeah.
Okay.
Sorry, I thought it was 4. Right. So basically, you take all the data now, and then you do all the calculations later. Right. So that's usually how we do these things. So you can run through the masses pretty quickly, but then moving on to the glassware. This is where it starts to get fun. So with our 10 milliliter cylinder. Oh, a little cutesy one. Where'd it go? Oh, over there. Be right back. Right, so we have our 10 mils here. So actually, I think I'm just going to, instead of pouring out of this big glass, I think I'm just going to use my transfer pipette. And just because it holds about a little over, if you fill it all the way up, it holds about 3 mils. Another thing you want to avoid, notice, I don't know if you can notice, you may get bubbles in here. So obviously, if you have a bubble, you're going to want to just tap it till it comes out. Till it comes, come on you. That is taking up volume, that is gas and not water. There we go. You can just keep tapping it till it comes out.
Which size do you want us to use again?
You use the 10 mil graduated cylinder, the 50,
Oh, okay.
the big one, and then we use the flask and the beaker. Come on, you. And remember, the key to this is to get down, get way down. So now I'm getting pretty close. So now I want to get my head aligned exactly with, I'm getting close. And there's not going to be much of a meniscus on this. This is so small that you're not going to have much of a bend in the water. The other thing you're going to want to avoid is having water. See, notice I have a drop of water on the, I've got a drop of water on the top. Now, that's not adding to the volume, but it's certainly adding to the mass. So I'm going to want to get rid of that. So I can just pull that. That's another good use of the transfer pipette. You can pull water out. There we go. Just get it out of there. So then I get down to that level, and I see I have a little bit more than 8. So what I will do is use my transfer pipette to take some out. Just a little bit. That looks pretty good. And then I just measure the, so you should measure the mass before and then measure the mass after.
How much water is going in the 10 milliliter beaker? Sorry, it wasn't.
I think it's 8. Was it 8?
It's 7.
7? Oh, I had, oh, damn, I had 8. Okay. 7, yeah. Of course, you should get the same error with 8, I would think. But when you, so when you subtract the mass of the graduated cylinder plus or minus the water, you should get around 7, or in my instance, 8. So I'm going to see what I've got here. All right, 18.97. Awesome. So mine weighed 10.99 grams empty. And then I got 18.97 when it was full. So that is really, really close to 8 grams. So you'll see that this thing is really, really good. You should get really close to your to the proper volume with this. You should find that this is the most accurate of all the different methods we're going to use. So so with the 50 mil graduated cylinder, same thing. Basically, it's going to be doing exactly the same way. And I think these balances go up to 100 grams. So we should be well within, because they weigh, this weighs about 29 to 30 grams. And we're supposed to put how much in there?
Good to see you here this late. Yeah, well.
How much goes in the 50? I can't. having trouble seeing it.
What are you doing here? I have a
24.
really annoying landlord that constantly makes me feel like
You're 35?
a chance to try.
Where is that?
I guess I'm so used to pushing myself. I just assume that
I think it's 24.
Did it say? For some reason, I don't see it now.
I don't need to.
Yeah, try. Yeah, I think. So what's the volume that goes in the 50 mil cylinder?
24.
24?
Yeah.
Where is that in the
Page 7.
page 7?
Yeah.
Oh, I went past it. There we go. I went past it. Yeah, 24. So that'll be fairly straightforward. What's going to be tricky is this. So this is the Erlenmeyer flask. Now notice it has only 2 measurements on it. Basically halfway and full. So it's got 25. So there's a bar at 25, and then there's a bar at 12.5. So basically what they're asking you to do is to try and figure out halfway in between. Because halfway in between would be like 17.25. So it should be a little bit less than that.
Is this table right here the estimated volume of water for the chart for number 2?
So what was the question?
This chart right here.
Having trouble. Somebody's got a TV going on or something.
This chart right here that you're showing. Is this the estimated volume of water?
Trust me, it was hard to find one who performed surgeries on someone my age who doesn't already have children, but
Okay.
you know me.
This is driving me crazy.
Love to fight. That's a pretty aggressive view. My mother died when she was 34. My grandmother when she was 32. That's why I pushed my.
Okay. So, sorry, the background noise was driving me nuts. So, whoever was had the question, just unmute yourself and ask again.
Yeah, I was just wondering this table right here. This is just confirming that, is this the estimated volume of water for?
Table 2?
Yeah.
Table 2 is the density of water. That's not the estimated volume. So what you do, so table 2, here's table 2.
Okay.
So basically what we do with that is, let's just do a quick experiment right here. So I've got my, where am I? So I've got my 25 mil flask here. And so they're asking me to put 17 mils in it. So I know that's going to be somewhere between the 12.5 and 25, slightly less than half. And so that's going to be really hard to do. So what I'm going to do is measure the mass of it. So the mass of my flask is 26.54 grams. So 26.54. So now I'm going to try and fill this thing to about 17.
I noticed that you're using a dropper.
Yep.
Are we supposed to be using a dropper? Because that wasn't on the.
Yeah, I suggested that. This is the transfer pipette. I suggested, yeah, because you've got a bunch of them in your kit. You figure you might as well use them because it makes much less of a mess than trying to pour. So it'll take me a minute to get there. But then again, you're just going to be eyeballing this. This is not going to be super, super accurate. We'll find out by how much. Okay. So I'm going to guess there. So when it was empty, it was 26.54, and now it is 44.65. So I don't have my calculator with me. So 44.65 divided or subtract 26.45.
Professor?
That's what, 18.2, something like that? So I use the 18, so if my volume, if my mass is 18.20 grams of water, I need to convert that to a volume. So I use table 2 to do that. So I figure out what my temperature is. My temperature was pretty cold. It was 15, now a little bit less. So I'm going to have to look up the density. But if your density, let's say it was 20 degrees. So your density would be right here at 0.9982 grams. You see that with the table 2?
Yeah.
You go to 20 and then you go over 1. So the density at 20 degrees is 0.9982. So I take my mass, which was like around 18.2 grams, and then I convert it to a volume using this density. That gives me an idea of what my error was. So if my volume is, if my mass was like around 18.2, that's pretty much what my volume is going to be as well. It's going to be around, it's around one gram per mil, right? They're all pretty close to that. But you want to be as accurate as possible, and this density helps us do that. Okay, so you see what the table's for? Was there another question?
What if you're getting 20.72 without the water?
Because my flask weighs something. I mean, it has a mass. Mm-hmm. So I just measure what the mass was before and after. Mm-hmm. You could also, just take the mass and then hit tare, and then do that. That works too.
I'm not following. So I'm on data table 2, mm-hmm. and I've done measured the mass of the empty, and then now I'm measuring the volume. So
right
on the instructions here, it says to measure, to put the graduated cylinder on the scale, mm-hmm. and then that's a certain amount, and then take it off, and then put approximately 7 milliliters of water, and then weigh it again. Is that right?
Mm-hmm. Right. So you take your mass of glassware with water and the mass without, and the difference will be just the mass of water itself.
So what number are we putting down on the volume? So like for example, the first one, it's going to be the total grams that is on the scale, right? Or is it going to be the difference?
Repeat that.
So for data table number 2, row 2, the volume of water, in the first column, 10 milliliter graduated cylinder, is that measurement of the mass going to be with or without? Is that going to be the total mass that's registered on our scale, or is it going to be the difference?
The mass of water will be the difference. So the mass of empty, basically you'll take the mass of glassware with water and subtract it from the mass of empty glassware at the top.
I don't understand. I'm sorry. I don't know.
So, so when we first...
The way that you're explaining it, I guess I'm not understanding it.
All right, let me hang on. All right, so for my 25, so here's my 25 mil Erlenmeyer flask. So I'm going to take the water out. So I'm going to measure the mass of it empty. So the mass of it empty is 26.62 grams. So then I'm going to try and put around 17 mils of water in here.
But wait, don't you record that?
I have recorded that. I just wrote it down, 26.62 grams.
Okay.
That's my massive empty glassware.
Okay.
Yep.
Yep. Okay.
And then I'm going to put my 17, I'm going to eyeball 17. Obviously, I'm not going to be super accurate about it. All right, so now I'm getting close. So I want to be somewhere between the 12.5 and the 25. That'll give me my 17. So I think it's going to be about probably about there. So now I measure the mass of it, and it is 45.27.
Okay.
So the difference is the mass of the water, right? I mean, here it's empty, here it's full. So the mass of water is going to be the difference. So around...
I mean, I'm trying to stop you or I'm getting confused, but you just keep talking. So I understand what you're saying, and that makes sense. But what doesn't make sense is after you were finished putting the water in, you didn't answer so you record that measurement, the 44 point something, that's what you put down as the measurement for that, right?
That's the mass of my glassware with water. So the volume of water is 17.
Row 2. Oh, the volume of waters. Oh, I see. Oh, okay. I understand now. All right.
And I really don't know what the high and the low volume is going to be. It's going to be somewhere, I think it's going to be somewhere like between probably 15 and 19, somewhere in there, because it's so hard to know. And these are just estimates that you'll be using yourself.
So do we record the God, do we record the weight of, what it weighed with the in it on the scale anywhere on our paper?
Mass of glassware with water. It's right here.
Oh, I see. Okay.
Yeah.
All right. Okay.
So then the difference, is the actual water itself.
What are we supposed to put for like high low volume? Like how do we calculate that?
That's not a calculation. That's going to be your estimate. So for instance, with the 10 mil cylinder, you're going to be pretty close. I mean, because if it's right on, let's say you've put it right on 7, I would put the high volume as like 7.1 and the low is 6.9. I mean, because it's right there. If it's right on the line, it's not 6.9 and it's not 7.1. So that's probably about as high or low in intervals as they're going to be.
Oh, okay.
That interval is going to get bigger the different thing you use. Like for instance, here with the beaker, every tick is 10 mils. It starts at 50 and then it's every 10 mils till you get to 100. So that's going to be a huge difference. I think we put like 35 mils in here or something? It's going to be really hard to figure it out. So I would put that as like, anywhere from 25 to like 45. It's going to be a big difference. But that's what you think, like how big could this really be? Or how small could this really be? That's basically what the high and low interval means. So the more accurate, the more ticks there are in between. Like if there's a tick every mil, you can probably get it plus or minus a mil. Okay. If it's every 1/10 of a mil, you can probably get it to every plus or minus 1/10 of a mil. But once you've got it to here with this beaker, it's every 10 mils. So it's probably going to be like plus or minus 10. So that's basically what it comes down to. Okay.
So is one
Thank
of
you.
the little marks 0.01 or point is like
On
for
the
like
on the 10 mil, it's every
Yeah.
0.1. Yeah, because notice there's 10 marks, or no, I'm sorry,
Yeah.
0.2. There's 5 marks for every between every mil. So each one of those is 0.2. So going from 9 to 10 is like 9.2, 9.4, 9.6, 9.8, and then 10. So each one of these is 0.2. And because the 50 mil is 5 times bigger, now the tick marks are also 5 times bigger. Instead of 0.2, now they're 1 mil each. And you can, that is actually, if you ever wonder what it is, that's actually written. Let me see if I can see myself here. That's actually written right on the top of the cylinder. It says 50 and then colon 1.0, meaning that every one of these marks is 1.0 mils. That's what that means. On the 10 mil cylinder, it has 10 colon 0.2, meaning that every mark is 0.2 mils. That's the meaning of those. Any other questions?
Okay.
I'm kind of confused still on how to calculate the
Volume?
volume intervals, because I have all my values, like everything is weighed on my chart, but I'm confused still.
Yeah, that is basically, like I said, sort of looking. So if you, like here with my 50, oops, oh, I'm running out of power. I left my, I might have to go soon. So if you go up to like 40 on this 50 mil cylinder, basically, and if you look at it, you can tell that it's definitely not 41 and it's not 39. So I would say that the error, the high and low volume interval would be somewhere between like 0.5, plus or minus 0.5, or plus or minus 1. It's sort of up to you to think how accurate you can measure with this thing. Can you measure it with like less than 1 interval? You probably can, right? Like half an interval above, half an interval below. So probably 40 plus or minus like 39 and a half and 40.5. That would be your high and low interval.
So once I have my mass and I have the temperature in my room, I use that to I use the equation to calculate the volume, right? From the chart.
Yep.
Okay.
And that goes into table 3. Okay. Yeah. So because then you have your actual volume, or measured your measured volume from your eyeball, and then the actual volume as determined from the mass.
Okay, so in those 2 rows, like high volume and low volume, are we writing like 0.5 plus or minus, or is that not what we're supposed to write? I'm kind of confused.
I think there would be like for instance the one that I said with, like, if it was 40 mils, that's on the 50 mil here. If you can measure it like with half a tick, 1 or above, that each of these ticks is 1 mil. So I would say the low volume would be like 39.5 and the high would be 40.5. And so that will give you an idea of what the uncertainty would be. But with this thing, there's going to be no idea. Like I tried to measure what 17 is here, but your high and low measure is going to be way off. That's why I sort of estimated like 15 probably for a low and 19 for a high, because there's no tick marks between the 12.5 and 25. So it's going to be way off.
What about, I'm so sorry. Where, at what point were we measuring the room temperature? And how do we get the room temperature?
Just look at your thermometer that you've got. You did get a thermometer, right?
Right.
There should be one in the kit.
Okay, yeah. Oh, so we don't record that. We just use that. And then
You definitely record that. Yes.
Where would we, and just
write it down
notes, or?
in your notes. Yeah.
Okay.
Yeah, I'm surprised there isn't a place on the tables for that. There really should be.
And then for data table 1, I just went back to it. It's just, we're just recording cup 1 and cup 2 on the scale with no water at all.
Right.
And then recording each one. And then what do we write in for the deviation from average?
So you calculate the average when you've got your 5 measurements. And then each deviation is how far away was each one of those trials, 1, 2, 3, 4, and 5. There'll be 5 separate masses, right? How far was each one of them from the mean or from the average? And those should be really small numbers.
Okay. Oh, so I put the cup on the scale 5 times. Oh,
Right.
I think. Okay. Thanks so much.
Right. And so your deviation should be really, really small.
Okay.
But let's look at table 3. I'm surprised there's no, they don't. Oh, current water temperature. Yeah, that's where you put your room temperature.
So I don't understand. That doesn't make sense to me. So are we measuring the temperature of the water, or are we measuring the temperature of the air?
Well, the water.
In the room.
The water.
Oh.
Yeah.
Okay.
Yeah, that's why I would sort of like wait for the water to sort of come to. So I suggest you don't take it right out of the fridge. The reason for that is that the water temperature will be changing over time. Like it'll be 4 degrees when you take it out of the fridge, and then then it'll be 8, and then it'll be 10. And so when you do the actual measurements of mass, that's when you need to know what the temperature is. So that's why I would just let the water sit in the room for like at least half an hour, just to let it equilibrate to the room.
Okay.
But it's obviously it's the temperature of the water that's the important thing, not really the room. Yeah.
All right.
Yeah.
And then for data table number 2, the last row, mass of water, is that, so are we doing subtracting the mass of glassware with water from, or we're subtracting the mass of empty glassware from the mass of glassware with water to get that?
Right. Mm-hmm. Yep. Yep.
Yeah. Okay.
And the volume is what you're estimating. So you put like approximately 7 mils in the cylinder.
Right.
The first cylinder, one was it 30 or 24 in the second one, 17 in the third, and like 35 in the last one. So these are all going to be your best estimate, and then you'll find that basically your precision is going to go down, down, down the further you go across the table.
For data table number 2, the uncertainty row, would that be like, for example, when we were doing the example of 50 milliliter cylinder, would in that box, would I write like 0.5 plus or minus? Is that like what we're supposed to write in that row?
I think it's the difference between the high and the low interval divided by the volume.
Oh, okay.
Yeah.
There's
what's that? The uncertainty?
Yes.
Yeah.
Yeah. So it'd be like the difference between the high and the low divided by the volume of whatever it is you're measuring. So for the 10 mil, if your difference is like half a mil or less, like maybe even be less. So your uncertainty would probably be somewhere around like, 5% maybe, or even less than that. It's basically how accurate do you think you could measure this? And you should, with a tick every 0.2 mils, you should be able to get within, like, I would say 0.1 mils pretty easily. So that would give you an uncertainty of around 2%. But if you don't think you could measure it that accurately, then maybe it's going to be a little bit more. But it shouldn't be much more than like 2 to 4%. And then it should go way up by the time you get to the beaker. Your beaker should be uncertain as hell.